Let's start it with the first data structure. Let me share a whiteboard first. So the first data structure is about a stack. So what is a stack? I remember for Python, see this picture? So for Python, right? I remember one of our current data structure is a stack. I think it's a list or array. I don't remember, but we're gonna figure out this after I explain this stack. So for empty stack, they have such behaviors or properties. Let's say push, and pop, right? So if you guys have ever tested our data structures or Python data types, I think list or array, they were kind of like the same, right? Where's the color? Oh yeah, so here, when I give in a list or initialize this list, right? I can append, for example, like a string into this empty list. So that list becomes a list of length 1, right? Which obtain a character called A. So this A becomes the first item, or at the end of this item of this stack, and then we can append, or we can use this function append. We can append a B after this list. So then the list becomes A and B, right? So this stack becomes A and B. So how can I get the how can I get a B or C, right? I can also have a C or a 1. Can I get the number? Can I get the number C? Yeah, we can get this number by its index, right? So the index is 0, 1, 2, and 3. You can get this number by 2. But if you operate this list by data structure, you can only have the operation, let's say the push or a pop. So what if let's say this list is called list, right? List 1. So what if I call a list 1 dot pop? What do we got? It's the last item of this list is this one, right? It's quite interesting. We have in Python we have another way to pop up these numbers, but in the other direction. Let's say we pop up the first item. I don't remember, pop the first. Yep. Yeah, not pop 0, not slicing, Deque, maybe pop 0, right? So by just call, if you just call the Python the pop, it will just remove this one. So the stack data structure have a property which is let's say last in, first out. So remember this, last in and first out. Right, but we have other types of data structure, right? Let me see, which is for example like queue. So we have what if we have a queue? So queue is like when we're waiting for some service, for example like a cinema, or you wanted to enter in some service, right? For example like in a dining hall. The queue is like our human being queuing in line. For a queue, they have two types of operation. The first is the in queue, the other one is the deque. So consider this. You might come up with the property of a queue, right? So what is the property of a queue? Can anybody guess for a queue? So it should be first in, first out, right? That means the the first guy have the most priority to leave this queue. So see here, first in and first out. Let's see what else. So deque is the operation that makes your elements out of the queue. In Python, I remember we have a package called queue, but we should import this by we have a, let me find some examples here. So import the queue, right? Let's try this in our. So by using the queue, you need to import this queue, these packages, and then you assign data structure called queue as queue.queue. So here in this example, they initialize some class or function like a worker, right? So some worker get to the company at what time, and he leaves the company when he finishes his job. So for example, for let's say 30 task, working on 0, working on 1, working on 2. Well, it seems no there's no Deque for this example. Might be. Let me find a Deque example. Well, this is just Deque. Let me find the Q first. Okay, maybe this one. But this one didn't use the package queue. So the initial queue is A, B, and C. So yeah, so another way to use a queue is still we can use the list. The differences is here. The way sorry, I cannot draw any annotations here. Sorry. The difference is we can use the queue.pop 0 to make the first item leaves the queue. Right. The other is the same. It's the same as the stack. Right. I've taught I've discussed before. In the stack we can use the pop, but in the queue we can use the pop 0. Another way is to use the queue packages, but I'm not sure whether they introduced this one. Let me see. Okay, so in this package, the way to dequeue, I guess, is using the queue.get. So by import a queue, in this example, we initialize a queue of numbers 1, 1, 2, 3, 4, 5, 6, and this is the head of the queue. This is the tail of the queue. So by using this queue.get, this queue was dequeued first, right? So I think this is the introduction to a queue and dequeue data types. Another types of data structures called priority queue. Yeah, so for a priority queue, we can have some intuition is, what if, let's say we are human beings, wait in line, but some other guys may, for example, like I wanted to pay more to get the first one to leave the queue, right? So everybody have a wallet or some cash that you can be paid to leave the queue. So for giving that giving that weighting factors. So each members of us have some weighting factors, right? So by using this weighting factor, we can draw a data structure, or let's say a tree, right? So for example, like this one, we can in Python we can use this heapify function. Let me find a example in Python. Yeah, so maybe the philosophy of this one is, so here we have a list that's 21, 1, 14, 45, and 78, and 3, and 5. So each one, I think it should be weighting factors. So by after the heapify, we got a priority tree, right? So I think the understanding of this heap tree is 1, 3, 5, and then I don't know, 78, and this one maybe 21 and 45. Right? What about this one? So the parent node is the 1, and left and right is 2 and 3, and then for this one is 4, 7, 9, 10, right? And next one is 8, 6, 16, and 14. So by using this heapify, we can give this weighting factors to each element of this data structure. So I remember there's an algorithm. It's called heap sort. That means, let me try to recall these materials. So let me see. Well, let's just check the time complexity first. Yeah, so heap sort is kind of a quick sorting algorithm. It's n log n. So heap sort is n log n. And how do we do that? Let me try to use this. heap sort Python example. So by giving a sort, an array like this, after running this heap sort is 5, 6, 7, 11, 12, and 13, which is sorted by this heap sort. Do you guys know we can use the sorted function like this in Python? Yeah, we can sort it by this, but this is the algorithm, right? We don't know the time complexity of this sorted, but we can calculate this or analyze this heapified or heap sort, right? I may not introduce heap sort in this section, but I'll just leave it here if you guys are interested. Yeah, the other one is tree. I think we have seen a lot of times of trees or graphs. And the most interesting topics is about graph. Okay, let's start from this here, right? Okay, for a graph it's kind of like social networks or Instagram, right? In real life, we know each other by this type of connections. But in graph, how do we describe this relationship by a graph, right? So assume we have, let's say, 2 or 3 students. It's called A and B and C. Another one is maybe a professor, right? A professor, Professor 1 and Professor 2. And some of the student might belongs to, let's say, the CSE department. And this professor is from CSE department too. So you might attend his class in the past. So you make some reach out or some connection with this professor, right? That means you know this guy. The other professor might be an ECE class or ECE department. And this student might attend this class, let's say ECE 30, right, in the past. And this student, he is a member of ECE department. And he has a connection with this professor. And these two professors may not know each other. And we have also let's say, AM applied mathematics professor is Professor 3. And one of this professor know each other, right? But this guy don't know this guy. So that is a graph, right? So just think of this as a social networks, right? How do we, let's say we started from here. How do we get all the connection between all these professors, right? How do we describe these things? Well, for a graph, we have 2 types of graphs. The first is the directed graph. the other one is the undirected graph. By the terms of directed means this connection you have with the professor or from each nodes, they have a direction, right? For example, like you know this professor by his name, by his fame, by his maybe his publication, right? You read a paper from his past publication, so you know this guy's name. But this professor may not know your name because you're a student, right? So for this case, you know his name, so this is just by one direction you know this guy. So this is a directed graph. And it's also possible this professor know your name because your performance very well in his class. So you know each other, right? This is bidirection. You know him and he knows your name. He's very familiar with your name. This is one case. That is directed graph. Another case is like the original one. There's no direction in this link. That is an undirected graph. Undirected graph means you can go from, let's say, started from A to anywhere through this path. You can go to this direction. You can go back. You can go back, go back, go back. So let's just assume this graph is a undirected graph. So there's a way to describe this kind of graph by a matrix. It's quite intuitive. So let's just assume we have some rows and columns. Let's say A and B and C, and Professor 1, Professor 2, and Professor 3. That is right, a 6 by 6 matrix, right? So how do we describe this graph by a matrix? Just assume if you know each other, you have a number of 1. If you don't know each other, you don't have the link, let's say, between A and B, the number is 0. So just, let's say, for example, A, he knows Professor 1, so here is a 1, and no other, so the other one is 0. So for example, like C, we know Professor 1, Professor 2, so here's 1 and 1, and other ones is 0. What about B? He knows Professor 2, other one is 0. And Professor 3, he knows Professor 1, and other one is 0. 2, he just knows C and B. So, sorry, here is 1, other ones is 0. And Professor 1, he knows 3, C, and A. Other are 0. So here's a quite interesting pattern. If you are figure out this, that is how do we say this? Sorry, adjacency adjacent matrix. Adjacency matrix. Right? That means by this diagonal direction, the elements from rows to the columns are reflected by this diagonal. You see? This is the same elements. Why do we call it adjacency matrix? Because when in a large matrix calculation, if it's a large matrix, we can only consider the upper triangle, right? And then we can eliminate some calculation the lower triangles. There's also, if we define this matrix by, let's say, let's say a matrix A equals this matrix. What is the property of matrix A power of 2, or matrix power 3, etc., etc., matrix power n? What is the meaning of the matrix multiplication? It's a little bit hard, but that means by multiple times, can we still, let's say C to the P1, can we still transfer my information from me to him? For example, let's say B and A, we don't know each other. How can we reach out to A by using this matrix? Maybe by several times, these values becomes a 1. That is something we don't need to know yet, but there's some properties here if you're interested. Just by using maybe the term adjacency matrix in Wikipedia, I guess. Here we have a matrix power. Here's a properties of matrix powers. So let's just read this this description. If a matrix A is an agency matrix of the directed or undirected graph, then the matrix AN has an interesting interpretation that the elements I and J gives the numbers of walks of length n from vertex I to the vertex J. If n is the smallest non-negative integer, such that for some I and j, the elements I and j of an is positive, then n is the distance between vertex I and j. Okay, you might don't know, but that is a quite interesting one. So this is just a definition of a graph. Another interesting one is the topological sorting. If you're interested, I can keep on talking. What is the topological sorting? So what is the topological means? If we're reading the books in CLRS, the example in this books is topological sorting. Is that if imagine you have you have a human, but you're naked at the morning, and this human is called professor, right? Whatever professor. And then if you wanted to, let's say, go to the class or classroom or to go to the office, what you should wear, right? Maybe you should wear, maybe you should wear a, let's say, a watch, right? Maybe you should wear a glass. Maybe you should wear a hat. Maybe you should wear your underwears, right? Maybe you should wear your socks. maybe another pair of shoes, and then trousers, right, maybe a t-shirt, maybe a gloves, maybe in the winter, maybe a coat, right? So that is the order, right? So for execute some things, right, you have some order to be implemented before you done before you done this task. For example, like if I wanted to, let's say, wear your shoes, what should be done first? We should wear socks first. Maybe I should, before wear the socks, maybe I should go to the restroom, right? Maybe I should wash my face, something like that. And then I wear the socks, and then I wear my shoes. But before I wear my shoes, maybe another one is I should wear my pants. So that means you have some priority before this task is handling. So this is this can form as a graph, right? By using this topological sorting, you can sort your events as a, let's say, top one to be done, and something you can finish by the end. That is topological sorting. For example, like when we install something, let's say install a matplotlib. If you're interested, you should figure out there's something like called dependencies, right? You can imagine this topological sorting is you wanted to install matplotlib, right? But your code detect that you lack some dependencies. This one you have, this one you have, this one you don't have. You need to install this and this first, and then you can run to install the matplotlib. So this is topological sorting, and it also has some interesting properties here. And if you guys don't know this book, I think I shared with some students in my previous sections. I can share this book to you guys. So you can see, if you're interested, you can find out the heap sort. The topological sorting, I think, is topo. I think it's a little bit too hard. Yeah, it's in chapter 22. So I don't think you guys should know this first. But anyway, if you guys are interested, maybe in this chapter, elementary graphs, topological sorting. It's in chapter 23 of this book, and this book is used in CSE 101. So I'm just quick scan this book. So this is the graph. This is the graph we just draw, and this is the adjacency list. This is the adjacency matrix I just draw. This is the definition of the matrix I just said. If there's a connection, there should be 1. If there's no connection, there should be 0. And I didn't touch the breadth first search or the depth first search. If you guys, anyone are interested, I can expand this these topics, but I would rather ignore that part. Yeah. Another one is the topological sort. I will share these book chapters to our chat box, and also to the Discord. But I don't know what our home assignment would be, but I felt it's a little bit too hard for you guys now to learn these materials. You see, this is the picture I just giving you guys. If a professor Bumstead topologically sort his clothing when getting dressed, and this is the graph, and this is the topological sorting. By analyze this, you get some lemma, you get some theorem. By topological sorting, which is you don't need to know yet. If you're interested, these numbers I remember is the time that we took to running this task. Oh, I'm sorry, I missed one definition. Is this is called the edge. This direction or undirected graph, this is called the edge, right? And the nodes below a graph or a tree. What is a tree? A tree is the materials that you traverse the graph. That is something you generated after you traverse a graph. But how do we traverse a graph is by using DFS or BFS. We have two types of method to traverse a graph. By using this, you can generate this type of graph, right? This is the order that you visit the graph. That is called a tree, right? We have discussed this tree in the algorithm analysis part, but this is the materials or format or data structure we can generate it after you visit the graph, right? That is a tree. Okay, I think that's all I can share with you guys. I will ending this recording, and if you guys have any questions,